My name's Sally Jordan. I'm Professor of Physics Education and Head of the Open University's School of Physical Sciences. I'd like to welcome you warmly to the 6th Annual Colin Pillinger Memorial Lecture. I'm sitting at my dining room table at home, which is in Norfolk in the UK, and this has been my work base for the past 9 months, and it's a particular privilege to be able to welcome people from all over the UK and indeed all over the world to this year's event. 2020 has been a very difficult year for many of us, but one of the benefits that's come has been a result of realising that our new way of working means that we can run this sort of event very effectively in an online environment. And of course, it's considerably easier and more environmentally friendly for this evening's speaker, Dr. Andy Spry, to join us in this way from the SETI Institute, rather than it would have been to fly him over to the UK. I'm going to hand over to Professor Pillinger, who's Colin's daughter, in a moment, and she'll set the scene more fully. We'll then have Andy's lecture, or a recording. We won't have the recording, I hope. I hope we'll have the real thing. And a question and answer session hosted by Professor Ian Wright. I would say we're monitoring the chat boxes in all the platforms on which the event is streaming, which is several. So do post your questions there, or alternatively, if you have a specific question for Andy, can you please email it to stemcommunications@open.ac.uk. That's STEM, STEM -communications@open.ac.uk. I just want to thank Andy for agreeing to give the lecture, the Pillinger family for working with us, and all the people who are working in the background this evening in order to bring the lecture to you. And now, without further ado, I'd like to hand over to Shoshana.
Thank you, Sally. And thank you very much to everyone who's joined. It's a miracle of technology that we're able to talk to so many people virtually, and I'll reiterate what Sally said, across the world. So as Sally said, I'm Shoshana Pillinger. I'm Colin and Judith Pillinger's daughter. And along with my brother Nick and the wider family, we decided that we wanted to do something to honour Dad's love of telling as many people as possible about science. He really enjoyed sharing the challenges and the excitement and the rewards of anything to do with science, research and exploration. Each year, since Dad died in 2014, we've held a public talk in his hometown in Bristol. And like many others, we've been forced to move our event online this year. But I'm excited that this is a new platform for us. I just wanted to say a quick thank you to all the guys at the Open University who've made this possible. There are a lot of people working behind the scenes, and it really enables us to continue Dad's legacy of science communication. So interestingly, we decided on a topic for today's talk before these strange times that we find ourselves in. So it's sort of a bit of an uncanny relevance that we find ourselves living under the UK mantra of hands, face and space. So stopping the spread of disease is really at the forefront of our minds at the moment on planet Earth, and planetary protection takes it that step further to another level. So we're pleased and grateful that we've got Dr. Andy Spry joining us today, a world expert in the field of planetary protection. Andy has degrees in biochemistry and began his career in medical device sterilization. And he became the planetary protection manager for Beagle2, which was Britain's mission to land on Mars, which was led by my father. And this was all back in a time, nearly 20 years ago, when PPE was needed to build a spacecraft, not to do your weekly shop. Andy, as Sally has said, is joining us from the SETI Institute in Washington, where he's now a senior scientist and planetary protection consultant for NASA. So I'd like to take this opportunity to say thank you to Andy and everybody else. And with thanks from the family in particular, I'm going to hand over to Andy, and I hope you guys all enjoy the talk.
So good evening, everyone in Europe, and good afternoon to those in the US, or even good morning on the West Coast. Thank you all for tuning in. I just wanted to, as the slides are coming up, to tell everyone it is a great pleasure for me to actually have the chance to give this sixth Colin Pillinger Memorial Lecture. It's 20 years ago this year that Colin and Judith first came to my company, and the question was asked, can you sterilize my spacecraft? And my manager at the time, after we had listened to the perspective of Colin and Judith and the plans and the sort of concept of Beagle2, my manager said, don't spend too much time on this, Andy. So I'd like to tell you at the outset, I ended up joining the Beagle2 team within 6 or 8 months of that activity. So I've spent pretty much the last 19 years doing a very niche activity called Planetary Protection. And what I'd like to talk to you about today is how that's mapping out with a look back and a look forward, the topic being Mars and other places that we care about, with a subtitle of Planetary Protection in the Commercial Spaceflight Era. So here's a little rundown so you can see the topics that I'm going to try and cover. What is planetary protection? Shu gave quite a good introduction there, but I'll kind of add some technical aspects to it. How did it work for Beagle2? A look back. Why do we protect places? Where do we protect? A little more history, especially looking at in the context of this being Moon Night. We'll look back at Apollo, the first planetary protection of a crewed mission. Then focusing on Mars as the horizon destination of space exploration by the agencies NASA and others. What do we know about Mars? What do we plan to understand more about Mars in order that we can answer that question, when is it the right time to get humans to Mars? So what is planetary protection? I'd like to sort of delve into science fiction for one answer to that. This is the sort of antithesis of the planetary protection we do from Earth, looking at it from the perspective of the Martians when they invaded Earth in H.G. Wells' War of the Worlds. They invaded Earth and did some pretty harmful contamination, but in the end, they themselves were wiped out by the microbiology of the Earth. So both from a forward planetary protection point of view, that's what we address when we're going to somewhere and taking our spacecraft with it. We're looking to avoid forward contamination of the destination. And then back contamination of the environment, we're exploring bringing it back to the terrestrial biosphere. In both those contexts, the Martian planetary protection guys didn't do a very good job. But trying to do a good job has been a recognition on an international level for many decades, first kind of captured at the international level as part of the Outer Space Treaty, which is pretty much every spacefaring nation, the three at the time were the US, the UK, and the Soviet Union, but every spacefaring nation since, and there are well over 100, and they're all signed up to comply with the Outer Space Treaty, and particularly Article 9 of the Outer Space Treaty. The red text there is essentially the planetary protection text that we're trying to avoid harmful contamination and also adverse changes in the environment of the Earth. And mechanically, how we do that, what do we do to achieve planetary protection? There is an organization called the Committee on Space Research, or COSPAR, that manages and maintains an international consensus policy under the Outer Space Treaty, and that is described by two sentences. Again, looking at the forward and backward contamination between the target and the Earth. And that is the conduct of scientific investigations of possible extraterrestrial life forms, precursors and remnants must not be jeopardized. and that's avoiding the forward contamination. Don't discover something we took with us and mistake it for an extraterrestrial. And then, in addition, and for most people in the audience, this will be the most important part, the Earth must be protected from the potential hazard posed by extraterrestrial matter carried by a spacecraft returning from another planet or other extraterrestrial sources. So how did that apply for Beagle2? Well, Beagle2 was a one-way mission, so we were really addressing the forward planetary protection. And for those of you unfamiliar, here's a line drawing of the Beagle2 lander and its assembly into a probe. What you can see in the left-hand drawing is two halves of a clamshell. The upper half in the center of the page has 4 petals, which were solar arrays. And in the other half of the clamshell, the lower right, that's packed with electronics, power, and scientific and analytical devices. And that bundled up together is the center component in the right-hand image, where that was placed into a front and back aeroshell, together with a parachute and some airbags. That's a fairly taxing space mass volume problem. And then that device at the bottom, very bottom right-hand corner, is an attachment to Mars Express, which was our bus ride to Mars from Earth. When we considered controlling the cleanliness of Beagle2 from a microbial perspective, in other words, managing that contamination, there are a number of choices on how you can sterilize any article. The problem with spacecraft hardware is some technologies actually destroy the article that you're sterilizing, so you wouldn't get it to work afterwards. So we had a delicate balancing act to do to try and sterilize the hardware to the right level, given the choice of available sterilization technologies. And so here are some technologies that are available: dry heat sterilization, gamma irradiation, gas plasma, and solvent wiping. And basically, we started on the left side and said, anything that can withstand that, we'll use that, because dry heat is well liked by engineers. So the structure, the gas analysis package, the arm, and the solar arrays were all sterilized by dry heat. Heating the parachute fabric, in particular the threads that held the fabric together, was going to weaken it. We didn't want a weak parachute, so we had to find another solution. Gamma irradiation was that solution. And for gamma irradiation, that's not very friendly to the electronics. So any electronics that weren't stable to baking and wouldn't work if you irradiated them, they had to be cleaned by a gas plasma process. So into that category fell the common electronics assembly, including the battery, the POR, or the position adjustable workbench, which is a scientific package, and the radar altimeter trigger, which had to work, otherwise we would have not opened the parachute and plowed into the surface at high velocity. So the next device, the pyro mechanisms that separated Beagle from the Mars Express at the right time, to actually have that occur, none of those radiation, heat or plasma technologies were known to work. And so that's the one group of devices that we resorted to a solvent wipe, which is a non-ideal approach because it's not as effective as the others, but that was the best that we could do, and it still got us under the bar in terms of how clean Beagle had to be. Once you've got the hardware clean, you have to keep it clean, and given that all of those devices were sterilized by different methods, we then had to reassemble them to be a whole spacecraft without recontaminating them. So we did that in an aseptic assembly facility, which was custom built for us at the Open University's campus in Milton Keynes. And basically, from the uncontrolled area shown there in the salmon pink, people or hardware will move through successive cleanliness levels until they entered into the aseptic assembly area, which was a class 10 clean room, many times cleaner than a hospital operating room. and the assembly work was done there by the scientists and technicians, particularly the guys from Astrium, who worked so hard on the spacecraft. I'll just show you that now. Here's some of the assembly and testing work going on. The bottom center there, you can see a test on the arm. The upper right, you can see a test on the lid closure. And when all that work had been done, the spacecraft, Beagle2 spacecraft, was flown to be tested with the Mars Express spacecraft, and then the whole assembly was flown to Baikonur in Kazakhstan on the Antonov that you see in the bottom right corner. Once we got it there, Mars Express and Beagle2 together went through a launch campaign, successively being mated one to another, being incorporated into a fairing, the pointy part of the rocket. And as you can see in the bottom center through the aperture in the fairing, that's the last we saw of Beagle, clad in its black thermal control layer, on its way to be mated to the Soyuz rocket that launched it from Baikonur. That was a 2 a.m. launch in June of 2003, and then we were able to report the cleanliness level of Beagle2 to the COSPAR organization and demonstrate that we had in fact achieved better than the requirement. COSPAR has spore requirements in their policy, which spores are a resting state of bacteria, a robust resting state that the bacteria, some species of bacteria enter if they get into an environment which is not conducive to active growth, and they're more resistant to killing, and so these are a good indicator. If you can manage the spore cleanliness levels, you can manage the overall microbial cleanliness of your spacecraft. You might have noticed that Beagle2 has an outside that would have been contaminated by the environment of Baikonur, and so we did account for that by utilizing the fact that as the Beagle2 probe entered the Mars atmosphere, it would have experienced very high temperatures, up to 1200 degrees C on the front center of the aeroshell, 200 degrees C on the back. And so we were good all the way to the surface in terms of the microbial cleanliness of the spacecraft. And of course, we didn't hear from Beagle2 after we had deployed the spacecraft on December the 19th. And since there were two American spacecraft flying at the same time, there was some speculation about in the media at the time about how that might have occurred. But of course, we didn't hear from Beagle until MRO, the Mars Reconnaissance Orbiter, spotted the visual images that gave us the final disposition of the Beagle2 spacecraft on the Martian surface, and we were so close. Anyhow, why do we do this thing called planetary protection? Well, if we're ever going to answer the fundamental questions of was Mars home to microbial life? Is it today? Could it be a safe home for humans one day? What can it teach us about life elsewhere in the cosmos? What can it tell us about the past, present, and future of Earth? Then we need to protect the ability to answer those questions. And you can't do that if all the time you have this haze of Earth contamination traveling with you. You need to be able to tell if Martian life is actually Martian, or was it something you launched from Baikonur or Florida, according to where your spacecraft launched it from. And that's part of our trying to understand where we fit in the sort of the solar system, and with, you know, within the larger cosmos. This is intended to show the sort of the sweep of time and our place in it as we move from purely chemical processes to biochemical processes to intelligent life. But in all this, there's a concept that life can't just evolve anywhere. There needs to be a right size, shape, history of the environment that life is to evolve in, and the Goldilocks concept of, you know, too sweet, too salty, just right applies to planetary protection. Too dry, too cold, and that's why the places we care about is not an especially long list in the solar system. This is showing together relative size, but not relative location. The three terrestrial planets, one either side of Earth, and Venus is too hot. Earth is just right, and Mars at the present time may be too cold, but Mars has a history with it, and as we understand more of that history, we understand that Mars did used to have liquid water on the surface. It may have had an evolution, separate evolution of life, and we'd like to know about that and understand it. So Mars, our nearest neighbor, is the place that we look to first to see, is there life next door? And as we sort of study that, we understand more about the conditions of life, what is habitable and what may not be habitable. And we see other places in the solar system which have some of those conditions. One is Europa, where it has a subsurface liquid ocean, which may be salty and briny, in contact with a rocky core, and an icy shell that, if we ever want to understand whether it has its own biosphere, we'd better not contaminate the subsurface ocean. So we need to be careful about how we reach the icy shelf, reach the icy surface, and go beneath it, travel beneath it. Another place is Enceladus, which is an icy moon of Saturn. Enceladus is much smaller than either Mars or Europa. It's only 500 kilometers in diameter, roughly. And the interesting thing about Enceladus is, at the time we launched Beagle, we didn't know that Enceladus had a subsurface ocean that was in communication with the surface. And this was spotted by Cassini during a flyby in 2005, where the ice crystals were being expelled from the surface of Enceladus, visible as a plume, and further investigation showed these tiger stripes you can see towards the south pole of Enceladus, which appear to be the vehicle or the path for the release of these particles. So anytime we're going to send a spacecraft to any of those three targets, we have a set of requirements from each agency, which is following the COSPAR policy or guidelines, and we're looking at controlling the number and the amount of microbial material that's present. So any number of different environmental microbes, you see some examples there on the left side, and basically we're trying to cultivate a small subset of them as indicators of cleanliness. And we do that using very classical 1970s microbiology, using Petri dishes. We haven't got to the point yet where modern genomic methods are as sensitive as just growing a single organism on a Petri dish. We do that multiple times per spacecraft. And here you see on the right side 2 incubators full of Petri dishes that were from the Mars Science Laboratory mission. Basically, some hundreds just from one day's activity. It's not that busy every day. This was a particular session of closing out activities, but there were hundreds of Petri dishes. And the other thing to notice that the clock in the top left corner of that image shows 10:45. And I can tell you that that's PM, not AM. They had really put in a full day's work to get that amount of analysis done. Here's some more images of the MSL project from the US side. You can see various different sampling activities going on, wiping and swabbing to collect the surface microbes from the spacecraft inside the belly of the rover in the bottom left corner. Before the launch of the rover on the Atlas V, you see there in the top right corner. So this is a montage of spacecraft which have gone to Mars or on the way to Mars from the US side. And I want to feature these because one of the features, one of the issues for us is that every time we send a spacecraft, we learn something new about Mars. One of the key things for the top left-hand spacecraft, which is one of the MSR rovers. The MSR rover's Spirit and Opportunity went to Mars at the same time frame as Beagle2, and in particular, the Spirit rover had a sticky wheel, which resulted in it dragging the wheel across the Martian surface. And at one point, they dragged the wheel, and it removed the very top surface, exposing, which is the red dust that we all associate with Mars, but it exposed a very white crystalline material underneath that we didn't know was there. So we're learning about the geography of Mars by accident. And the bottom left corner is the Phoenix lander, and just underneath you see 3 images taken over time of the Phoenix lander leg underneath the rover, and you can see speckles in different places, and those speckles are the light-colored speckles are water which was melted from the ice underneath the lander as the lander arrived, and condensed on the leg of the lander and stayed liquid, sufficient that it could move around. And that was a first indication that Mars is not too cold for liquid to be present for some time, even at the surface. In the center image there, you have the MSL rover, and that in its landing at Bradbury Landing took itself into Yellowknife Bay, which for the first time helped us to understand the long-lived liquid water lake type, lacustrine type, lake type environments that had persisted on Mars for perhaps tens to hundreds of thousands of years, and really highlighted through its observation of essentially a dry lake bed, a dry riverbed, the processing of the geology there to turn sharp pebbles into rounded pebbles, the same way as we see on Earth in where streams and rivers have been present for a long time to generate rounded pebbles. The bottom center picture is InSight. The InSight lander is kind of a younger brother to the Phoenix lander in terms of configuration, but InSight took a mole to Mars, a mole very similar to the one that was deployed or planned to deploy from Beagle. But when it was deployed on Mars, after 20 plus years of development on Earth and testing and getting it to work perfectly, it didn't work at Mars. It wouldn't drill itself in. And so there's something different going on with the physics associated with particles, either electrostatics or gravity related, that we really don't understand very well. So again, another thing that we learn new about Mars. Top right-hand corner is an orbiter that went to Mars. The other 5 and 6, if you include the Mars 2020 Perseverance rover and helicopter, Ingenuity helicopter, that one is an orbiter, but that one still had to be cleaned because its passage through the Mars atmosphere on its way to its orbit meant that it was extreme risk, if we didn't understand the atmosphere as well as we thought we did, that may end up being a lander also, albeit at very high velocity. So that lander also had to be, that orbiter also had to be managed from a microbial contamination point of view. And then just to highlight the one that's the odd one out, the one that's not still at Mars, this is a rendering of the Ingenuity helicopter, and in the distance the Mars 2020 rover Perseverance, which is going to take the first samples of Mars ready to bring back to Earth, so the start of a Mars sample return mission. But I'd like to take a diversion to the moon for a minute. The Apollo missions did planetary protection, and they were intended for the 11, 12, and 14 missions that we would protect against recontamination of the Earth from the moon. Now, just show you the image there, just the bottom text there. We didn't go to the moon to find life. We didn't think the moon had its own biosphere. But in the interest of the public safety and in the interest of public confidence, it was decided that the right thing to do was to manage the contamination risk from the astronauts coming back and bringing the lunar samples with them. But it wasn't a perfect solution. It wasn't a solution that you would say unambiguously no lunar organism could have made the trip. It was about a risk reduction activity, but if there had been a lunar organism, what would have happened if the capsule had sunk? What would have happened if the astronauts had ingested it? Well, the astronauts ingesting it, they made their way into an isolation chamber, but it was via the deck of an aircraft carrier with other humans present. And you can understand in these days that social distancing is not being observed between the diver and the 3 astronauts coming out of the capsule in that left-hand image. And even though there was a guy in the orange suit spraying bleach after the astronauts had traversed across the aircraft carrier deck, there may have been opportunity for leakage. And so this is my opportunity to actually do the public service announcement and say, you know, the things we learned from Beagle, you saw the guys in the suits with masks. That level of PPE wasn't typical for 2002, 2003, the same way as it is for 2020. But the things we did learn about contamination management with Beagle and also with Apollo is that, you know, masking works, and keeping things clean works. Wash your hands, and social distancing works, and also avoiding crowds. One thing I didn't say in the Beagle image is we limited that clean room with that clean spacecraft to 4 people. So that was our effort at limiting the crowd in the Beagle environment to limit the contamination risk. So that's it. Public service announcement over. And we're on our way to understanding more about Mars from a crude perspective. We're doing that in 2 steps at NASA. NASA is going back to the moon with the Artemis series of missions, and with commercial payload providers using the CLIPS program, which is a commercial lunar payload service, where essentially NASA or others can buy space on a lander system to take a device to the surface of the moon as a path to making a viable economy out of space exploration in a way that we haven't been able to do to date. And so, you know, there will be a per pound rate for sending an instrument or yourself or granny's ashes to the surface of the moon. One of the things we're doing with that is to revisit the endpoint of the lunar planetary protection from the Apollo period. Apollo said the moon has no life, so we will not protect it. But we're understanding from the moon and its resources, it has a science activity that is possible to help us understand more about the history of the solar system. There are ice deposits on the moon which are thought to give an indication of the history of the solar system the same way as ice cores do on Earth in Antarctica. So we're wanting to protect that. So we're looking at how we right-size planetary protection for the moon when we don't have a a concern about an extraterrestrial life form as part of the picture. But going back to Mars, we do have that concern at Mars. And bringing a sample back is the best way to get the best analysis. We have sent instruments to Mars to try and understand more, and we've learned a lot, but we've always found that the instrument you want to send to really do the analysis is like too heavy, or requires too much power, or you need too many samples for the available space on the spacecraft. So the best way of studying Mars is to bring a sample of Mars back to Earth. And that's different from the meteorites that fall naturally, because we will understand where the sample came from so that we can understand the geologic context and be able to place the analysis in a context, rather than having to guess from something that falls from the sky what the history of the environment, the original source environment of that rock is. So this has been going on for a while. Mars sample return has been the most important mission of the next decade for several decades now, and it looks like we're finally trying to get to it, with Mars 2020 actually planning to take samples. But just to highlight, this is from 1976, and we haven't done it yet, but this is the current plan. Mars 2020 is there on the top left-hand side. It will take these samples, put them in tubes, and then we will have to send 2 launches actually to get enough spacecraft hardware to bring those samples back. The first one I'm going to address is the sample retrieval lander, which is a US-led mission with a rover from ESA. So the sample fetch rover will be flown by the sample retrieval lander and go and collect those tubes and deliver them to an orbiting sample container on the ground at Mars. That's at the top of a Mars ascent vehicle, so a rocket basically to launch from the surface of Mars. When the sample container is full, it'll be closed up and that launch will occur, and the orbiting sample will be released into Mars orbit, where a second spacecraft will collect it and bring it back to Earth. The second spacecraft is the Earth Return Orbiter from ESA, and that will do 2 things. It will seal the orbiting sample in a containment system which breaks the chain of contact between Mars and Earth. That's very important, so that anything that was on the outside of the orbiting sample, Mars dust, for example, will actually be encapsulated in a robust system which will be sealed all the way to Earth. Then the orbiting sample will be transferred in its contained state into an Earth entry vehicle, and the ERO will deliver that back to the Earth atmosphere before diverting itself with the Mars contamination into a heliocentric orbit, an orbit around the Sun. So by doing that activity, I think we might get some clue as to whether there is life on Mars. I'm not in the school of thought that there was intelligent life on Mars. I'm not sure we're going to find Marvin the Martian or identify culprits that were hiding their civilization from our explorers using cardboard cutouts of Mars. Mars landscapes. What I think is more likely is going to be at the microscopic scale, something like we see in Antarctica, where the microbiology has retreated inside the rock to protect itself from the hostile environment, but it actually makes a good living there. It likes it. So that's my sort of best guess to what the thoughts are about life on Mars, leaving it in the Mythbusters sense as being plausible. And if we assume that, then we still need some sort of planetary protection. So even as we get to the point where we're thinking about sending humans to Mars, and I'll say that NASA is planning this, it has no direction from the Congress to spend significant amounts of money making it happen, but it is planning for this in the 2030s timeframe. And this is a description of the current Moon to Mars scenario for the first crewed mission on Mars. It's being studied for up to 6 crew, and they're all guys on there, but I'm willing to bet that when it comes to the actual flight, there will be ladies present as well. And how we do that is under review. But what we're looking at in terms of the hardware to take there is a Mars transit vehicle, which will allow us to safely take a crew to Mars and bring them back. The capability to land when we get there, and then the capability to leave the Mars surface and return to the Mars transit to come back to Earth, because the astronauts do want to come home. We're looking at how we will do that in the context of cislunar, deep space, and Mars orbit as learning environments before we actually go to the Mars surface. The earliest time that this works practically from a NASA point of view, if you should assume current levels of funding and current other commitments to do other activities, is the 2030s, but only just the 2030s, 2039. And I ought to have said in the previous slide, the Mars sample return activity, those 2 launches, the ERO and the SRL, are scheduled for launch in 2026. With the orbiting sample returning in 2031. So that gives us 8 years or so to figure out what it is that can be learned from a returned Mars sample to inform how we would do the crewed exploration. But the crew will be away from Earth for 2 to 3 years, depending on whether they opt for a short or long stay. The orbital dynamics means that Earth and Mars are orbiting in different rates. So there's a narrow window for launching from one to the other, so that you will actually arrive in Mars or Earth's orbit at the time that Mars or Earth is present for you to land there. So 30 days is one window, roughly 300 days or sols is the other. The reason for the mission is, you see the left-hand icon there, to look for life, but also to understand geology and climate science, everything that we can about the Martian environment that we can explore better with an astronaut's hands rather than a robot. The how-to is planned currently for a 2-phase activity, one where we send stuff ready, so a pre-emplacement of the box there is intended to depict random stuff like food, like the science instruments that you would want to use. Then you would also need robotic support to actually get that pre-deployed material unboxed ready to use. In particular, the power system. So we need to have power deployed. And we also want to have ready and operational the Mars ascent vehicle, so that as soon as the astronauts land, they can actually leave if they need to. Then the second phase would be a lander habitat with some kind of sealed transport to allow efficient use of the time, allowing the astronauts to more quickly rove across the surface, and then the crew themselves. That's the current concept. And here's a rendering of how that might take place. You can see a lander concept there and a rover concept with 2 crew unloading something useful. That would be a 30-day mission in the current plan, with only 19 days of those available for exploration before they had to get ready to come home. So the planning activity is key to make the best use of those 19 sols, or roughly 190 hours outside the capsule on the Martian surface. One of the issues with sending crew is that you have a different problem to the robotic missions. Robotic missions, any contamination, microbial contamination that's there, that's what's there. But with crewed systems, they're just bigger, so there's more of it. And the other part of that equation is that the crew themselves, and the fact that the crew environment is maintained like an Earth-like environment. Higher temperature, higher humidity, breathable atmosphere. Those are all environmental factors which are helpful for terrestrial microbiology to grow as well. So you have the bioreactor of the crew and the bioreactor of the crewed environment, which would break the robotic exploration paradigm, where you have requirements for maximum numbers of spores delivered by the spacecraft. And so we're going to have to evolve that strategy so that we can explore Mars safely, both from the crew perspective and from the perspective of Mars. And one of the ways we're looking at doing that is to try and define boundaries where currently Mars is considered as a monolithic environment. But the more we have been there, we have understood that Mars is not Mars. There are very different environments in Mars. And so some of those will be not contaminatable, and some of those may be contaminatable, and some of those may be inhabited also. And so we need to have this segregation of environments at Mars, different environments at Mars, to try and understand, to try and separate those two things so that we can keep our astronauts safe, but we can actually do our exploration without contaminating Mars. Here's that concept folded into an exploration zone, which is the concept of how the astronauts might explore, where you have a safe zone, which is in the middle of a larger area where you have resources that the astronauts could use for long stays or regions of interest for science. And so how do we get from the current robotic paradigm to the paradigm for crewed exploration? Well, the real issue is that we need to know more about Mars. So we have, under the COSPAR umbrella, the space agencies, NASA, ESA, JAXA, others, the academic community and the spacecraft engineering community have been meeting together over a series starting in 2015 and still going. Although virtual meetings are challenging, it's much better to meet in person. But here we've identified a suite of knowledge gaps. We've identified what order we need to address those knowledge gaps to actually make the knowledge available in the right time frame, using what missions, to make what measurements, to make sure that Mars is protected for future exploration, and to make sure the terrestrial biosphere is protected. Now, I did say this was in the context of commercial exploration, and obviously one of the commercial companies that has been very successful in launching spacecraft from Earth is SpaceX. And in the time of Beagle, when we were doing planetary protection for Beagle, they didn't really exist as an organization. They hadn't even launched the Falcon 1 at that point. But now they've made huge strides in terms of their capabilities. And this depicted on this slide is their end goal, where you have paved roads that lead from launch pads to essentially a large greenhouse where all of the colonists, as opposed to explorers, are going to reside. But I just want to highlight the, as it were, the elephant in the room. Why are you doing all this planetary protection stuff for a Mars mission in 2039 when Elon Musk says he's going to send colonists in the mid-2030s? And I'm just going to draw to your attention that I think Elon Musk, for all that he has achieved, is operating on a different timeline in terms of what he's promising at the first instance versus what he's been able to deliver when all the wrinkles are sorted out. And this quote from the Wall Street Journal in 2011 says, "I'll put a man on Mars in 10 years." But at the moment, Starship is at serial number 8, test pending. Looking forward to the success of that, but they're still a little bit behind that original timeline. And part of the reason for my sort of position in this, that it's just going to take longer, is because Starship is only the launcher. You can launch people to Mars, but they won't still be alive when you get there, unless you do a whole bunch of other stuff the kind of things that have been addressed on the space station for the last 20 years or so to keep the people alive. And that is a whole bunch of work. And just highlight it here. Here are the exploration capabilities, or the capabilities for keeping humans alive. Each one of those boxes are interconnected to one another. So every time you move one, you have to adjust the other. And so this suite of interrelated systems has been developed over 20 years, as I said, with the ISS. And we get those to work only by having the ISS only 250 kilometers away from us, so we can bring stuff back when it breaks and fix it or send a new one. And that's not possible in the context of a Mars mission. Everything that is needed for the crew to survive has to work all the way to Mars and all the way back. And that's a no small task. So that's all I wanted to say. I just wanted to leave you with this other slide, which is an image drawn by or painted by David Hardy, a print that was given as a leaving present to me as I left the Open University to come to the US, depicting Beagle2 on the surface of Mars and Colin in his spacesuit. So with that, I'll wrap up and hand over to Ian.
Thanks a lot, Andy. What a fascinating talk. You covered an enormous amount of ground there. And what I'd actually like to do in a minute or so is to get the people who are on the local conference here to unmute their microphones, and we'll give you a round of applause. But before I do that, I think in light of, there's been a Pillinger Memorial lecture. I mean, there's no more fitting tribute to the man, and I hope you don't mind me saying this, that basically your work with Beagle2 and Colin and so on has basically defined your career. And, in a way that he has done for many people in many different ways. Anyway, can we unmute our microphones? And we'll attempt to give you a round of applause.
Well, I've learned something new today. I didn't know you could do a virtual round of applause in reality.
So yeah, we've got a few questions here. One thing I'd like to just ask at the start is that, I mean, you said planetary protection is a niche business. Just in case there are any youngsters who are watching, I mean, how would they get into it?
So you can't go to a university and say, I want to take a course in planetary protection yet. Everybody who's in planetary protection came to it via another route. For myself, it's biological sciences, but for others, it's actually been nuclear physics. The current planetary protection officer at ESA is a nuclear physicist by training. And the real issue is you need to find a way into a space agency to cut your teeth, as it were, in how space agencies work. And then once you're in the door, you would align your career with the opportunities that are available. So planetary protection is a very current opportunity. Folk at ESA and NASA are looking at life scientists with interests in astrobiology and extreme organisms in extreme environments to adopt them into the planetary protection discipline, to do work in planetary protection, to make sure that we're doing the right thing. But those are the sort of paths: some kind of scientific specialism, some kind of interest in the space agency activity. And then really you can steer your own career from there.
Thank you. I've got a question here from Terry Ransom. You probably remember Terry worked on the mission, Beagle2. And what he's asking basically is, given all the pain that some of us went through with planetary protection and so on, I mean, how do you feel about the privateers and their attitudes to what might happen when they explore places like Mars?
So I'll make an observation. There have been 2 interplanetary missions by privateers. And one is the test launch of the Falcon Heavy, where a inert dummy payload was substituted quite late by a Tesla Roadster of uncertain provenance from a cleanliness perspective. And it wasn't fired at Mars, it was fired to Mars distance. And that was kind of not managed well from a compliance perspective. The other example is the lunar Bereshit mission, which was an Israeli launch, where payloads were provided but not fully declared. So a person who styles themselves as a space pirate stowed away some material on the Bereshit spacecraft, which was biological in origin, and sent it to the moon. Now, the moon we don't care about actually from a planetary protection contamination with viable organisms point of view, because it has no biosphere of its own, and the organisms, when they get there, are not able to contaminate the environment to the extent that we would either lose science data or lose use of the environment through contamination. So if they just said, can we put these things on? The answer would have been yes. But the issue is they didn't follow the process. And so at least in the US, there is a sensitivity within the government, within the space agency, to try and manage this a little bit better. But we certainly don't want to get to the point where the red tape is getting in the way of doing good science. I mean, that's not the point of planetary protection. The point of planetary protection is to make sure we do the right science and get the right answer. We don't want to get in the way of that. But there need to be constraints on how clean certain hardware is when it's going to these sensitive targets like Mars, Europa, and Enceladus.
Thank you. You actually answered a question there that someone else had asked. Paul Dickinson was asking about the tardigrades on the mission and how on Earth, dare I say, could that be compatible with planetary protection? I have a question of my own, and that is, do you think? I mean, I'm hoping you have a stock answer to this. I don't mean it to be a nasty question. I've spent my life studying Mars in the form of Martian meteorites and so on. So of course I want return samples from Mars in the lab to study. But do you think, with things the way they are, with a global pandemic and the sort of distress and disease and death that the whole population of the world have been suffering, that do you think this might dent the enthusiasm of humanity to some extent for bringing samples that might contain life from another planet?
If you were to look at that only from a rational science point of view, the origin of the COVID-19 disease had a specific path where many exposures of humans to those kinds of viruses had not resulted in a disease, but one did. And that's that kind of biological fate, issue of fate was really a numbers game. And the same doesn't apply to how you bring back samples from Mars. Mars dirt has not been incubated in a sort of a vehicle, another animal vehicle, which can then be transferred to humans. And essentially what we're getting is Mars dirt, probably the at the numbers of grams level, and that's going to be contained really, really well in its vehicle ride back through the Earth's atmosphere to protect it against opening before we get it into a containment environment. And also, once it's in the containment environment, we would very much want to protect the Earth from the Martian sample, but also to protect the Martian sample from the Earth, so that we continue to get that separation of the two environments, so we can understand the Martian environment. And that level of containment it's what we do in labs every day for years on end, where we can actually protect those environments from one another, whether it's a contagious disease or a science environment where you're just wanting to study something in one environment and protect from the ambient environment. So yes, I think at the emotional level there are issues that need to be addressed. I think mainly they can be addressed by public understanding, a public education kind of outreach activities. This is what we're planning to do. This is the benefits of doing it. This is the end point of not doing it. We think the risk is at this level, and the transparency that goes with that. I don't think you're going to persuade all the people, but I think in the end it's a sort of a majority consensus that will allow the mission to go forward. And within the spectrum of people who are studying, valuing the study of Mars or valuing our trajectory of going to Mars, there are people on the extreme ends. That there will be people who say Mars needs to be protected and don't go there, and there are people who are saying let's go terraform Mars. We can do it tomorrow. And there's a spectrum in the middle. I think it's going to be the same for Mars sample return, but I think by having good communication with the public and a transparent process, we can actually get to a point where the public is accepting of what we're wanting to do.
Yes, thank you. We're kind of running out of time here. I'd just like to sort of ask you one final question, which is, do you have any happy or otherwise memories from the Beagle2 era and the planetary protection thing? I mean, it was a hell of a challenge convincing people. Or not convincing them. I think everyone was convinced, but just getting them to engage with the whole process. I mean, one of my own personal favourites was the engineers who are used to working in clean rooms and all that kind of stuff. They're not afraid about anything like that. But what they particularly wanted or needed to do was take their paperwork into the assembly facility with them. And of course, paper wasn't allowed. And this was a major cultural issue, I think.
Yes, I think I think it's von Braun said it. We know we're ready to launch our rocket when the pile of paperwork certifying that it's ready to launch reaches the height of the rocket. So yes, the space business is driven by what has historically been a pile of paper that says yes, we're good to go. This test worked. That test worked. We're ready. And part of that process was actually, to do that activity for the Beagle spacecraft, and we worked hard in an environment where largely pre-smartphones, pre-VPN environment, where the sort of proof positive of a system working was the right set of signatures on a piece of paper. And we kind of pushed on that. I do have one fond memory of that. There's a saying, in engineering, that sometimes it's better to ask for forgiveness than permission. So we did have for the clean room at Milton Keynes, the aseptic assembly facility, a rule of no paper, but the engineers had a whole list of adhesives that they had to mix in different proportions to one another to make them work properly. And if you got it wrong, the adhesive wouldn't work and the spacecraft would fall apart. But they couldn't memorize it all, so they put a piece of paper in a sterilization bag and sealed it up, so that the paper was never exposed to the clean room was never exposed to the paper, but I only found out about it afterwards. So, credit to you guys, the job was well done.
Look, Andy, thank you very much. Thank you again. It was a great talk. Really enjoyed it. And there's loads of questions on the meeting chat here. Everyone's had
so
a great...
I have a day job, but if somebody else wants to sort of filter those questions and feed them forward, I'll answer as many as I can.
Thanks again.
Thank you.